So now, let me give you a form. This is also important. The form of the propagator in terms of energy eigenstates, okay? And that's important because, after all, the propagator, the Hamiltonian plays an important role in the propagator, right? And what I'm doing right now are things I've done over the course, but in a scattered way. So I'm just bringing everything, all these observations together. Okay, so our propagator is x u t minus t0 of x prime, right? So now suppose that we introduce some energy eigenstates n prime labeled by n prime. So here it's this. This is an energy eigenstate n u t minus t0. And here another set of energy eigenstates n prime x prime. Okay? So now we are going to have n prime. This guy is going to act on, say, this or this. Let's say it's acting on this guy. So we are going to get x n. And remember, the explicit form of this is e to the power minus I by h bar. But instead of h, we will have en, and then t minus t0. And then we will have n prime from these two guys. And then we will have n prime x prime. But this is nothing but the Kronecker delta n prime. Well, if this was an integral, then this would be a Dirac delta. So this is more of a symbolic thing rather than, it can be generalized for the discrete case, the continuous case. So if I do the n prime integral or sum, then I have left over just one sum n, and that is going to give me this thing. What is this? This is just, if I write the energy eigenfunction at time 0 at psi n, this is just the energy eigenfunction at time 0. And what is this? This is the energy eigenfunction at time 0, but now it depends on x prime, and because it's the other way around, there's a star here. And then we have e to the power minus I by h bar en t minus t0. Okay, so, and then we can write this as sum over n psi of n x e minus I h bar en t, and this as psi over n x prime e to the power minus I h bar en t naught, the whole thing complex conjugated. So this is nothing but the stationary state. Remember, stationary states are energy eigenstates which evolve in time in a very predictable way. And we can write this at psi of n x t, and this guy is, the next guy is psi of n x prime of t complex conjugated. Okay? So this is another form of the propagator. So when the propagator is acting on my random state, so alpha at x of t is given by, as I showed above, delta x prime k x t x prime t0, and then alpha of x prime t0. But this thing is just given by this expression. So we can write this as integral over all of space, and then there's a sum over n, and psi of n xt psi star of n x prime of t0, and now we have alpha x prime t0. Now we can exchange the integral and the sum, and then this thing does not depend on x prime, so we can pull this out of the integral, and then we have d cubed of x prime, and inside the integral we have psi star of n x prime t0 alpha x prime t0. So this, we can write this as sum over psi of n x of t d of cubed of x prime. This we can write this as n x prime. This we can write this as x prime alpha t0, but this guy and this guy together just gives me the identity operator. So I have alpha at time, alpha of x at time t is nothing but the sum over n weighted by the stationary states, and this is just n alpha t0. That is the coefficient in the expansion of alpha along the nth energy eigenstate, right? Right. What is this? This is if I take alpha t0 and I expand it in terms of the energy eigenstates n, then I will have some coefficient Cn, right? And that coefficient is exactly this. So this is another expression for the propagator, where the propagator, you don't really see it explicitly, but it's hiding in the energy eigenstates. Okay. So, quantum mechanics is just a very, very, because of its deep connection to linear algebra, it's very, very beautiful. It's, the same thing can be formulated in many, many different ways. I just find, and in different, contexts, you have different techniques. I just find the whole thing extremely beautiful. I hope that in time you do too.